kind of 2 pointers. There's this other pointer here called fop. Anybody know about this? This is the so every time you open a file, files are many different things on a Unix machine, such as pipes, such as special devices, and each special device has its own list of file operations that can be performed, because not everything is the same. We're not running a Plan 9 machine. So this is a pointer to the file operation structure for this specific file, for this specific FD that we have open. And by the way, what's a file operation structure look like? Well, it's just an owner and a list of function pointers. Okay. So following fop, okay, is fcount, the number of times it's open, flags, some generic BS about the file descriptor, and fmode, the mode that it was opened with, and then there's like a whole bunch more crap after that too. But so let's take a best case scenario here. By the way, why is this the best case? This is the best case because it's at the beginning of a frame boundary. Okay. It's right there, ready for us, okay? This is why this is the best case for us. It's at the start of a slab. There is no slab metadata there. And just kind of for reference here, each block in here is 1 pointer size. Just so you know, right? To give you an idea of scale. By the way, nothing else in this presentation is to scale. So what's the really, really best case? Well, the really, really best case is that our string just so happened to line up before our struct file, okay? It's at the start of a slab, and it came from the same, and get zeroed page comes from the same kernel pool that the slab allocator grabs from. The slab allocator uses get zeroed page or something very much like it, and the sysfs buffer allocator uses get zeroed page. By the way, I'm going to talk a little bit more about that frame allocation mechanism in a moment. Okay, so what's a struct file look like? This is what it is, right? But, and I've darkened this time the parts that the kernel can survive for a little while with being smashed, okay? It's not, the kernel isn't going to survive forever. If you do a lot of operations on this file, it's going to be bad. If you exit the program, it's going to be bad. If you don't clean it up later, it's going to be bad. The kernel's probably going to crash. But there's only one pointer in here. There's only one member of this struct that really matters, And that's fop. Great news. That's really good news, okay? That means that we can pave over this struct file if we want, okay? We can pave over the beginning of it, we can pave over the end of it, as long as we get something that we're okay with in that file operation structure, okay? As long as we get something that we're okay with in that file operation structure, the rest of the struct file can be smashed for a little while. Okay, we're 1 for 3. Let's kind of get back to why we're doing this here. What are the 3 controls that we're going for? We're going for length. We're going for contents, attacker-controlled contents. We're going for an attacker-controlled target. The length is not an issue anymore, all right? We still don't have control over the length, but we found some place that it doesn't matter. We can go over by a little bit. Not, we can't go over into many, many struct files. But if we kind of open the number of sockets very, very carefully, we can go over by a little ways without causing the system to blow up and die immediately. So what's next? We have length. Let's try and control the content. All right. So here's the code that we're going to try and exploit again for your reference. Your string plus equals printf, stir, and then a bunch of format string for those of you in the back. So we can't write arbitrary content with this, right? ba2stir always produces a MAC address for us. %d always produces a decimal. %x always produces a hexadecimal. All of this is controlled by them, not controlled by us. The good news is that we can open sockets with the properties that we want, right? So it's very easy to predict the content. So if we open a bunch of sockets directed to nobody, bound to no socket, with no data pending, blah, 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 then if we cat this file, we're going to get a lot of stuff that looks a lot like that, okay? Null MAC address, 2, 0, hex, blah, 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 repeated a bunch. How many times is that repeated? That's repeated as many times as we want, okay? What does this mean? What does this mean? Data, all right, so data that, what this means that data that looks like that is going to end up in the file structure. If we go down this path, data that looks like that is going to end up in the file structure. No matter what else happens, that's gonna happen. So we better make the most of it. And what does that mean for FOP? Well, it means that a substring of that, 4 characters of those, if you're on a 32-bit machine, 4 characters of that is going to end up in FOP, no matter what happens, all right? So, well, what can go in FOP anyway? What does it make sense to put in FOP? And can we have this go in FOP? The stuff, one of those substrings, okay? One of those substrings. Can we put that in FOP safely? The only thing that matters from right now is to make sure that something that makes sense shows up in FOP. Something, it's the only thing we care about in struct file. Without something that makes sense showing up in FOP, the gig is blown. All right? We're done without it. So we better make it good. How are we going to do this? Well, FOP is just kind of a pointer into the kernel's address space, okay? FOP is a pointer into the kernel's address space. It's dereferenced by the kernel, and since the kernel thinks that it controls it usually, it doesn't do any checking on it, and that's okay. That's all right, because the kernel is supposed to be controlling this. What's interesting about that? The kernel's address space is a strict superset of the user's address space on x86. On x86, it is a strict subset of the user's address space. And so that means that it would be okay if FOP was a pointer into user memory. It would be okay. It doesn't have to be a pointer into kernel memory. So let's come up with a little bit of a game plan here to get this pointing to something reasonable in user memory. We're going to take this string that we saw a moment ago, that string, and we're going to map all of the substrings of it to become something valid of an FOP target. Okay? So for each of these, so the first substring is 00:0, and in ASCII that's going to be hex blah 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 blah. We trim off the end and make sure that that address points to a valid FOP target. Okay, 0:00, right? And we're just going to keep walking through the string for every member there. Bam, 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 bam. We're just going to keep throwing it along there, and we're done, right? We have this string sitting here. We now have data written there, and we've mapped that there. This is mapped in user space. We're using mmap. You know, we control that. We have, I don't know if you can read that from way out back there, but the pointer's inside there. So owner is null. That's okay for an FOP structure. And let's think about some of those other pointers, some of those function pointers. Maybe llseek should go to attacker ring 0. Maybe read should go to attacker ring 0. We're done, right? Well, not so fast. In reality, it probably looks a little more like that. Maybe there's going to be another frame in the way there. And now, instead of having FOP point to this structure, we have just some random bogus crap pointing to the structure. FOP has not been touched. We haven't won yet. Okay. 3 controls. Length, content, target. Contents aren't controlled, but we've predicted them. We've got length and we've got contents handled. Let's hit up the target. Let's be buddies. So how are we going to control the relative placement of these frames? We know that the whole idea behind this is the heap spray. Remember, we talked about that before, but we can't allocate that many FDs. we can allocate 16,000 FDs, but that isn't going to get close to the 128 meg of RAM in the VM that I'm going to be using today to demo this for you. And it's not even getting anywhere near the 4 gig of RAM that a small server nowadays has. Heap sprays are hard now. So let's talk a little bit about how memory gets allocated. I promised you earlier that I was going to talk about this. It's physical frames are allocated using this concept called the buddy allocator, okay? The buddy allocator, it's called that because it pairs up frames, and it pairs up groups of frames, and it calls them buddies and merges them. And this is a really, really old algorithm. This is from 1963. According to Knuth, who was the one who wrote about it, Markowitz was the guy who wrote it down, and I think it was actually invented late 50s. So this is a really old algorithm, but it turns out that if we use things like slab, okay, this goes really well with slab, because we're not having all of that fragmentation in memory of different sizes. So the implementation of this lives in Linux MM pagealloc.c. This is 4,000 lines of really, really, really well-tuned code, tuned to the weird cache infrastructures of Alpha, x86, ARM, Itanic, run in goddamn fear. You don't want to read it. Get a copy of Understanding the Linux Kernel. It's got a good description of it. That book is my god now. But what's important about the buddy allocator anyway? So with a run-of-the-mill frame allocator that's just grabbing frames, there's no real ordering to those frames. Okay? If it's just grabbing a whole bunch of frames, there's no real ordering to it. So this is going to inject determinism, predictability into frame allocation that otherwise we'd just be picking frames at random. We'd really have no way to determine what frames are going to be next. And the reason why it does this is it can allocate groups of frames of different sizes. And when it's able, it'll try and put a bunch of frames, one-off frames together so that it leaves as much memory wide open for big groups as possible. The implementation details, totally beyond the scope of this talk. I guess if I hadn't talked about slab earlier, I could talk about it. But I really think slab is cooler. So you guys can go look up the buddy allocator on your own. All right, what are we going to do? What are we going to do? How are we going to make this work? We're going to try and use this localizing technique here. And in brief, we're going to go fill up memory. And that means that everything that would have caused a discontinuity, it's going to get paged out. It's going to get paged to disk. Every other program on the system, paged to disk. What are we going to do to generate contiguous chunks? Well, we're going to free stuff. We're going to do this little alloc free alloc dance to get contiguous chunks of memory. And what are we going to do to allocate chunks of memory for our struct files? Well, we're going to free a little bit in there. And that's going to happen. We're going to allocate our buffer page, okay? Allocate our buffer frame, I guess I should say. And how are we going to do this? Remember, this happens when sysfs opens the file, okay? And the write hasn't happened yet. You can do the allocation without causing the smash to happen. This is critical. All right, we're going to pick up some memory for struct files here. Ready, aim, fire. What do? Memory starts off kind of looking like this. It's fragmented. There's other people's memory all around, okay? Luckily, we can allocate about as much memory as we want, and that's exactly what we're going to do. All of the system's memory, minus the stuff that the kernel needs, goes to us now. There's a lightly used machine that nobody's really paying attention to if you rootkit it, so it's not really using. There's not a whole lot of other stuff using memory. So everything gets paged out, and we're going to do our little free and allocate dance to make that all contiguous. You couldn't really see a change there, but now the frame allocator has those all kind of lined up such that if we free 4 in a row, then we get 4 physical free frames in a row. So what are we going to do next? We're going to set up our file.